Peter Selinger is going to talk about a finite alternation result for reversible Boolean circuits.
Okay, thank you very much. So circuits. So Boolean circuits, as you know, are built from gates and or not. Ubuntu 16.10 has experienced an internal error. Okay, and a Boolean circuit, of course, has whoops, to learn how to use the pointer here. It has some inputs. Often we take the circuits to just have a single output, but of course they can also have multiple outputs. And so a circuit really describes a function from 2 to the n to 2 to the m, where 2 is the set of Booleans. And sometimes the function is reversible, meaning invertible, okay, and sometimes it's not. But the point is that Boolean circuit, you could imagine that n is equal to m, and that that the function that you're describing here is actually a bijection between the inputs and outputs. But even when this happens for Boolean circuit, then the sort of components of the circuits are not invertible, just maybe the circuit as a whole. And in reversible computation, including quantum computation, you want all the components to be reversible. So for this reason, people look at reversible Boolean circuits. So these are usually built from also from gates, okay, but this time we use reversible gates as the building blocks, and the three most common ones introduced by Toffoli are the NOT gate, the C-NOT gate, and the Toffoli gate. And this is what we usually write for these gates. And what they do is, well, the NOT gate just negates the Boolean, and the controlled NOT gate, or also known as the C-NOT gate, would negate x if and only if y is equal to 1. And then the Toffoli gate would negate x if and only if y and z are both equal to 1. Okay? So it's relatively straightforward to see that a reversible Boolean function on n bits can be decomposed into these three gates. Okay? This can always be done when n is less than or equal 3, and then when n is greater or equal 4, you can only do it for even permutations. So a reversible Boolean function is a bijection on a finite set, in other words, a permutation, and permutations can be even or odd. Like, it doesn't matter if it's on the set 2 to the n. A permutation is even if it can be written as a product of an even number of transpositions, right? And of course, it's easy to see that if you take, for example, this Toffoli gate here, and you add a fourth wire where it's just the identity, a fourth input, W, okay, then of course, this gate would always perform an even permutation on the 16 possible states, because it will always map 0 xyz to something, and then it would map 1 xyz to something, and because it describes the same permutation on the 8 inputs that have w equals 0 as on the 8 inputs that have w equal to 1, it's always got to be an even permutation. So clearly being even is sort of a necessary condition if you're going to have any finite set of generators. If you have a finite set of generators for reversible Boolean circuits, and the largest generator is on n bits, then on n plus 1 bits, you always get only the even permutations. Or in other words, the whole group is not finite. The whole groupoid is not finitely presentable. All right. So for various reasons, I'm interested in generators and relations. So of course, reversible Boolean functions form a group, or more precisely, a family of groups, because you have one for every n. So the reversible functions on n bits. And they don't just form any family of groups, but what's known as a groupoid, in fact, a monoidal groupoid. What this means is that if you have a reversible function on n bits and a reversible function on m bits, then you get a reversible function on n plus m bits in the obvious way by performing the two functions separately on each of the two sets of bits, right? So you get a monoidal category where all the morphisms are invertible. And that's nice when you talk about generators and relations. Usually when you are talking about just a single group, you might talk about some generators for the group. And then once you have the generators, you might talk about equations that the words in the generator satisfy. And if you're lucky, there would be some finite set of such equations that would sort of imply all the other ones. But of course, if you have an infinite family of groups, you would sort of need generators for each of the groups. So a typical example that you probably know is permutation groups, where you have, say, a permutation on n objects, and then it has n minus 1 generators, which are just swapping adjacent objects. And then the relations are well known. The Yang-Baxter relations, you have sigma I plus 1, sigma I is equal to some other thing, and so on. But the point is that you need sort of, if you have n objects, then you need O of n generators, and you need O of n, at least O of n relations. But when you talk about it as a groupoid, when you also take the monoidal structure into account, then you just have a single generator, which is to swap two elements, and you can just tensor that with identities on both sides to get all the other generators. So that's why the groupoid structure is often sort of useful. Okay. Now, in the case of reversible Boolean functions, I gave you sort of the Toffoli generators. So in general, where you only get the even permutations, but that's fine. We can live with that. But there's actually no complete set of relations known for these generators. So if I give you two of these Toffoli circuits, okay, not only is it difficult to decide if they're equal or not, because that has got to be at least an NP-complete problem. You can just reduce the same problem for ordinary Boolean circuits to the reversible one. So, but we don't even know right now a complete set of relations for these. Okay. And why is this a non-trivial problem? It turns out there are many classes of circuits for which this problem of finding generators and relations has very easy answers. And they're subgroupoids of this groupoid we just discussed. The simplest example is the one I already mentioned, permutation circuits, where you take as generators just these swap gates. So that would take a pair of bits and actually permute them. And you can implement that. You can implement that in terms of these C0 gates like this. And other examples where the question of generators and relations is easy are linear circuits. These are the ones that are just generated by C0, so no Toffoli or negation gates. And the affine circuits you get when you also add the negations. And then in quantum computing, there are all kinds of sets of gates. I'm just mentioning here Clifford circuits. That's some quantum group where the problem is also easy. And what all the easy classes of circuits have in common is that they can be described recursively. Okay? They all have an easy and unique normal form. Normal forms are great if you're looking for generators and relations, because then you need to write down just enough relations so that everything can be converted to normal form. So an example is permutations. Here's some arbitrary permutation circuit, but you can use local laws. Here I'm applying some laws locally, and you can prove that in fact every permutation circuit can be uniquely written in this normal form, which is a certain staircase pattern at the beginning, and then recursively a permutation on n minus 1 bits. Okay, and you can, moreover, it's really easy to show that there's some finite set of relations by which you can convert everything to this normal form. Okay, another example where the normal forms are unique and easy is linear circuits. So remember I said that the linear circuits are the ones where you just have C0 as the generator. Okay, so these correspond exactly to functions on n bits that are linear as functions over the vector space, when you regard the Booleans as GF2, right, the two-element field. So in other words, of course, linear functions on n bits can always be described by an n by n invertible matrix where the entries are zeros or ones. And moreover, every such matrix can be quite easily and uniquely transformed into the identity matrix by applying Gaussian elimination. So you look at the leftmost column. If the upper thing is not a 1, then you permute some columns. And if it is a 1, then you use that to eliminate. You look at the bottommost 1 in the first column, and you kind of bubble it to the top, replacing each one along the way by a 0. And that gives you, again, this sort of staircase pattern, which is what you need to fix the first column in Gaussian elimination. And then recursively, you do it to the rest of the matrix. So you get this recursive structure of the circuits. So we can prove stuff about n-bit circuits by recursively proving stuff about n-1-bit circuits. And that is exactly, when we have such a structure, then we often have a canonical form. which is recursively defined. We can reason by induction, and then we get rewrite systems for converting the circuits to normal form, therefore making the equality easily decidable. It's then easy to find generators and relations, and sometimes the normal forms are actually minimal. That's not always the case, but if it is, then that's also nice because it gives you a minimization procedure for circuits. Of course, which we cannot hope for in general, only in these easy cases. So exactly what makes reversible Boolean Toffoli circuits difficult to reason about is that there is no such known canonical form and no such known way of reasoning about the circuits recursively on the number of bits. Usually when you are given a reversible Boolean function and you wish to convert it to a reversible circuit, then you write down the truth table of that function and you do something, basically fixing one input at a time to the correct output. Okay, so that's not by recursion on the number of bits, but by recursion on the number of inputs. Of course, you get an exponentially large circuit, but that's unavoidable because if you count how many there are, some of them have got to be exponentially large. So question, even if we can't have unique normal forms, can we at least reason by induction on the number of bits somehow? Is there a way to do that? And the result that I would like to tell you about today is really just sort of this little result here, okay? It's not going to solve the next 99, important problems in theoretical computer science, but I think it is kind of a cute result and I don't think it was previously known. So for n greater or equal 4, every even reversible function on n bits can be written as a composition of at most 9 reversible functions on n minus 1 bits, which are as in this diagram here. So first you operate on the bottom n minus 1 bits, then on the top n minus 1 bits, and you repeat this 9 times. Okay? Of course, it's not remarkable that every even function on n bits can in general be decomposed into parts acting only on n minus 1 bits. That we already know. For example, the Toffoli generators, right? It can already be decomposed into those. But rather what's remarkable is that the number 9 here is completely independent of n. Okay? Even if you got 1024 bits here, it can still be done with only 9 alterations. Okay? And I don't think that 9 is the minimal number that makes this theorem true. I think I proved that so a lower bound is 5. Okay, you can't do it with 4 in general. But I don't know, someone more clever than I will probably soon find a way to do it with 7 or even with 5. But 9 is sort of what we have.
But the pattern, the top or bottom, depends on n?
You can fix that you want to start with bottom, for example, and then it's still true. So you get one decomposition that starts with bottom and another one that starts with top, and they both have length 9. So in particular, if you want to compose 2 of those, you can always arrange it so the middle one cancels out. So then you have 17 alternations instead of 18. So what could you do with a result like that? I was sort of looking, there's not really a killer application, okay? But I'm imagining, if I'm looking for generators and relations, for example, I could take an arbitrary Boolean function and first write it in this form, and I could, if I find enough relations that would allow me to convert any circuit to one of alternation depth 9, then I could recursively use the relations on n-1 bits to bring those further to sort of normal form. That's just a wild idea. It doesn't really work because these normal forms are not unique. So you also need additional relations to convert any of the non-unique ones into any of the other non-unique ones. But at least it's a first step in that direction. It also gives you an upper bound for the size. It's another way to actually synthesize a reversible function into a circuit because first you write it in this form and then you recursively use the same algorithm on n-1 bits to do it. So you get O of 9 to the n as an upper bound for the size of the reversible Boolean circuits. That's much worse than the existing upper bound, of course. But it's nice because it has this recursive structure. Yuri?
So on the picture you omit upper bit and lowest bit and upper bit and lowest bit. Is it how you, in general, there are only 2 bits that are omitted, either the upper.
That's right.
or the
You
lower.
use the top n-1 and the bottom n-1. Yeah.
So it's much more special than.
It's not just any n-1 bits, but those particular ones. Yes. Okay. Now, in fact, you could state a slightly more general theorem, not much more general, but the thing to note here is the 2 to the n minus 2 states of the middle n minus 2 bits. Instead of using 2 to the n booleans, you could use any set A, right? Even if the cardinality of that set is not a power of 2. So consider, let A be any set with at least 3 elements. Then every even permutation of this set can be written as a product in this form. That's the more general theorem which implies the other one. But once you think about permutations of a set of the form 2 cross A cross 2, that gives you a kind of geometric way to think about the problem. Okay? So imagine that the set A, we think of the set A as the points in this rectangle here, right? And then 2 cross A means 2 copies of A. If X is any set, 2 cross X means you could visualize it as 2 copies of X stacked on top of each other. And you could visualize X cross 2 as 2 copies of X stacked next to each other. And then 2 cross X cross 2 would give you sort of 4 copies of the set A here. And a permutation of the form F cross 2 would be a vertical permutation applied. So the point is that you apply the same permutation to these left 2 copies of A and to the right 2 copies of A. And for 2 cross G, it's just the other way around. So every permutation can be written as a product of at most 9 of these forms, every even one. And because this is so nice and visual, I made this into a game, okay? So if you're bored right now and you don't really want to know the proof, you can go to my website here and you can play this game. There is a version for Linux and Mac and Windows, okay? And I will play it, later. I'll show you after we do the proof, okay? And it just allows you to move in exactly those ways, and the goal is to fix to get the right permutation in the end. Okay, so outline of the proof. It's basically very combinatorial. Combinatorial proofs can be boring, so I'll just go through it quickly, and then we'll play the game, okay? The way that we can do this in 9 alternations is first we use 5 alternations to fix one thing, and then we use 4 alternations to fix the rest, okay? So what we're going to do in the beginning is we're going to put all the, let's say, tiles, okay? Because we're thinking of this game. In the first 5 alternations are going to be used to put all the tiles, all the top tiles in the top and all the bottom tiles in the bottom, okay? So let's just think of all the top tiles as white and all the bottom tiles as blue. We're going to say that a permutation is standard if it's already fixed. So white is at the top and blue is at the bottom. Then we're going to say that a permutation is symmetric if the blue and white pattern on the left is equal to the blue and white pattern on the right. Now it's pretty obvious that every symmetric permutation can be turned into a standard permutation with a single vertical move, okay? Because you gotta have the same number of blues on the left and on the right, so that's definitely as many as you need. So in fact, a permutation can be standardized in one vertical move if and only if it's symmetric, right? Then we're going to say that a permutation is regular. So look at the vertical columns here. There's only 4 patterns that a vertical column can be. Blue, blue, white, blue, blue, white, or white, white, right? Of these 4 possibilities, we say that the permutation is regular if each of the 4 possibilities occurs an even number of times. For example, here I have 2 blue blues, and I have 2 white whites, and I have 4 white blues. So and 0 blue whites. So each of the 4 possibilities occurs an even number of times. And of course, when that is the case, then you can always transform this to a symmetric permutation with a single horizontal move, because those pairs always move together in the horizontal move. And we sort of go, similarly, okay? The next ones are along similar lines, slightly more complicated maybe to wrap your head around. We're going to say it's nearly standard if it's standard except possibly for 4 columns, okay? So here these left, this one, and that one isn't standard. If there's at most 4 counterexamples, then we say it's nearly standard. And you can prove that every nearly standard thing can be transformed to a regular thing with a vertical permutation. And then we say it's nearly symmetric if it's symmetric except maybe in 4 places. And finally, we say it's fair if it has got an equal number of white and blue tiles. because surely that is a necessary condition for being able to reach, the final state from the initial one. And then the proof just shows combinatorially that in fact you can start from any fair permutation and do this until it's sorted, okay? So in fact, I have not used 5, I've only used 4 alternations so far, because that's horizontal, vertical, vertical, horizontal, vertical. The 2 vertical ones can just be combined into a single vertical step. So we still have 5 alternations left. So now we know that all the top tiles are on the top, all the bottom tiles are on the bottom. Now we need to orient those tiles, okay? So we can use a single horizontal permutation to just fix the tiles on the top, put them all into their correct position. And now we still have to perform an operation of the form tau plus the identity, right? Apply some g here at the bottom and the identity at the top. And then we use, again, combinatorics. A permutation is balanced. Every permutation has a cycle decomposition. And it's unique, okay? You can uniquely write every permutation as a disjoint union of cycles. And then we say it's balanced if for every k there's an even number of k cycles, okay? And this is an example of a balanced permutation, and this is an example where it's not balanced. And the lemma is that if tau is a balanced permutation, then it can be written of the form a horizontal move followed by a vertical move followed by a horizontal move. That's relatively easy to imagine. If you had a balanced permutation down here, then you have 2 copies of each cycle, so you just move one of those copies to the left and one of those copies to the right, okay, in matching places. You can use a horizontal move to do that. And then you're going to use a vertical move that just doesn't touch the top half at all, but just fixes this little square here, okay, applying those cycles, the same cycles on the left and on the right, and then you can conjugate them back to their original positions. So, and then the lemma that makes the rest of it work is every even permutation on a set of 5 or more things can be written as a product of 2 balanced permutations, okay? So again, this is sort of combinatorics. You just do it by case distinction, and with that, we have actually finished the proof, right? So this is the end of the main theorem. And now all that we have to do is actually, I have to prove it to you now, right? So let me reshuffle it randomly, okay? So I'm not cheating here. So does this trick work? So we have to move all the blue and yellow backgrounded tiles to the top and all the orange and green backgrounded ones to the bottom. So first we have to make it nearly balanced and so on. So look at all the pairs of a tile and a matching tile. So here we have blue, blue, okay, and yellow, yellow. So that's up, 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 up. We're going to pair those up. Then we have, here's a yellow. Here's an upper tile and a lower tile. We need to find a matching one somewhere. Here's an upper tile and a lower tile. So these two match, these two match. Here we have an upper and a lower. Here we have an upper and a lower. Here we have a lower and a lower. And here we have a lower and a lower. So I'm lucky actually because it really was randomized. This time it's already, whatever we call this, it's already balanced, okay? So if I move, so let me do horizontal moves now. If I move this one over here, and I move, it's more fun if you do it yourself, actually. But maybe you'll watch me do this. So now it's symmetric, because I have the upper, 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 and the upper, 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 upper. So I can change my direction of moves here, and bring all the yellow and blue stuff to the top, and all the green and orange stuff to the bottom, okay? Now I can reverse directions again. By the way, this little app is actually counting not just the number of moves, but also the number of flips, okay? Because that's what we can minimize. Okay, now you fix the apple and the orange. And, oh, this is really lucky because the, for some strange reason, the strawberry was already fixed. You can calculate the probability of that happening. That's absolutely randomized, okay? I did not make it do that. And now we have to fix the bottom thing. So we have to write whatever permutation that is done here as a product of two balanced permutations. If we look at it, we have to move this guy here, here, and here. So this is just a single 3-cycle actually that I have to do now. How can I write a single 3-cycle as a product of two balanced permutations? I'm going to swap these two guys and, for example, these two guys. That's balanced. And then we're going to swap these two guys and again these two guys. That's also balanced, right? So swapping these two guys and those two guys is easy. Okay, that was the first of the balanced permutations. And now I have to swap these two tiles and simultaneously these two tiles. So I need to conjugate the left-hand side. This messes up the top, but only temporarily. Now I have to swap these two and these two, which I can do with a horizontal, with a vertical move. And then finally, I can unconjugate, and congratulations, we've actually done it with 6 flips. Okay, so in this case I was lucky and I only needed alternation depth 7, okay, rather than 9. So, yep, that's basically the end of, and there's more puzzles here. So you can, if you know how to do the easy one, try that one, right? And I made it easy for beginners. So in the beginning, because, it's not so easy actually if you don't know the proof. In the beginning, you just have fewer colors, and then, so my kids really like playing this too because, it's easy in the beginning. It only gradually gets difficult. So thank you. Yep, that's all.
Questions? It somehow has the flavor of like the algorithm for solving a Rubik's Cube.
It's a little bit similar to the algorithm for Rubik's Cube, yes. So not quite, because in a Rubik's Cube, you're looking, in a Rubik's Cube, you've enumerated finitely many what they call algorithms, finitely many of these moves that, for example, allow you to swap 2 of the cubies or 3 of the cubies or something. Here, in the final step, you do have to look at the whole permutation and sort of look at the cycle decomposition. So that's a little bit more than just applying a finite number of patterns. But of course, you could solve this also with a finite, like there's just a move that you can do to perform, say, a 3-cycle. And then you could decompose every permutation into 3 cycles. It wouldn't give you a bounded alternation depth if you did it that way. But it would allow you to solve the puzzle. I mean, the point of the research part of the talk was really the finite alternation depth. But for people trying the puzzle, they might not care so deeply. They just want to get it done. Right. Any other questions? Yes?
So the lower bound of 4 alternations, is it for your pattern or is it for any pattern where you use just n-1?
The lower bound of 4 alternation? I think the counterexample uses a 3-element set for A. Already that you can't do with 4. Yeah. And of course, if you can't do it for some n, then you can't do it for any bigger n either, I think. It's not entirely trivially true, but I think that's true. Well, intuitively, the problem should get harder when n gets bigger, but it could get slightly easier in the beginning because you got more dimensions for temporary scratch space or something. Okay.
Is that an easy argument to prove that you need only finitely many flips?
Not that I know of. I mean, the argument I gave is not super difficult, but I don't think there's like a one-liner that would prove even finite alternation depth. So that I talked to reversible computation people, and some of them didn't seem to think that that was plausible even. Certainly wasn't. Certainly it's not obvious. It would be nice to have already short proof for some n, right? And then use all the technicalities just to get n equals 9. By the way, I lied a little bit. Well, I didn't lie. I just omitted a detail which I, out of pure honesty, will tell you about, which is that the permutation that you are decomposing had to be even for obvious reasons. That's obviously a necessary condition. But these little white rectangles that I construct here are not themselves even. They might be odd, okay? So if you want to use that method recursively, you need to have even alternation depth of 9, meaning that the f's and the g's are themselves even. For that, I'm able to prove that as well, but I can only do n equals 13. I can do it with 13 alternations, but not with 9, okay? But I think that's not at all tight. I would conjecture that you can also do it with 9 for the even case. But I just wanted to mention it, full disclosure. Okay, no other questions? Yes or no, Dominic?
When can we expect this to be released as a phone app?
So I have patented it, and I'm working on making a JavaScript version so it can run in your browser. I think that's the way to go if you wanted it to actually become, I don't want to say viral, but like if you wanted people to actually try this, it's got to be in a browser and it has to have a button to share your result on Facebook. It's the way. So there's a provisional patent on it right now because I thought it would be fun to try and see if at least I can make enough money to get the costs of the patent back.
Is it public?
It's public, yes, yeah. So
where is it?
on that website that I mentioned, on basically my homepage. Sorry, you can't see that from over there.
That's fine.
/pgame. I haven't come up with a real good name for the game yet either. Surely it can't be called Permutation Game if it's going to be for the public. So, but anyway, right. Thank you.